In this video, I'm going to show you some examples of how to find the limit as x approaches infinity or negative infinity. So as I mentioned in previous videos, when we have a rational function and we're trying to find the limit as x approaches infinity or negative infinity, we can divide the numerator and the denominator by the largest variable, by the variable with the largest exponent. So when we take a look at our denominator here, that would be x squared. So we're going to divide our numerator by x squared, and we're going to do the same thing with our denominator. So when we do this, we get 2x cubed plus x squared minus 1 plus 1 over x squared, all divided by 3 minus 5 over x plus 7 over x squared. So as I mentioned before, any of the terms with x squared on the bottom, as x approaches infinity, we know that this will become 0, this term will become 0, and so will the 7 over x squared. So all of these become 0. All right, so now what happens when we plug x as infinity? So we can see that our numerator has some x's, and we would plug infinity into x cubed and x squared, but our denominator stays the same at 3. So since the numerator gets larger and larger, but the denominator stays the same at 3, we would say that this limit goes to infinity. So I'm going to let's write this down. So the numerator gets larger and larger, but the denominator stays at 3. All right, let's take a look at another one. So we'll do C here. So we again look at our denominator, and we see that the variable with the highest exponent is x cubed. So we're going to divide our numerator and our denominator by x cubed. So let's write limit as x approaches infinity. So this time we get 2 minus 1 over x plus 1 over x squared minus 1 over x cubed, all divided by 5 plus 1 over x plus 1 over x squared minus 5 over x cubed. So again, the terms with the denominator of 0, all of these 3 on the top, all of these 3 on the bottom, they all become 0. So I really only have left the limit of 2/5 as x approaches infinity. So since there is no x value, that means that my limit is always going to be 2/5. All right, so which of the functions above have horizontal asymptotes and why? So based on what I've done so far, just on A and C, A doesn't have a horizontal asymptote because it goes on to infinity, but C does because it actually approaches a number. So we would say that C, because the limit approaches a numerical value. All right, let's take a look at some other limits. These ones have radical functions in them. So we can actually do something very similar. Okay, so we have a radical. Now, we again look at our denominator because these are rational functions. And we see that we have an x squared and we have a plus 1. So we would say that in the denominator, the variable with the highest exponent would be x squared. So what I'm going to do, I'm not going to divide by x squared, but I'm going to divide by root x squared. So when I do this, now remember the root x squared is actually just x. So then we have x divided by x, we have 1 in the numerator. Now when I do that in the denominator, I would be dividing each of these individual terms. So if I actually rewrote this out, as a rational like this, I would actually be dividing each of those terms by x squared, because I can actually think of this as one big radical and have this as x squared plus 1 divided by x squared. So writing it like this, I can see that x squared divided by x squared would be 1. And then I would have 1 divided by x squared. Okay, so using the fact again that this 1 over x squared becomes 0, I only have 1 over 1 left, which is equal to 1. All right, let's take a look at another one. So we'll take a look at C again here. So this time we have a cube root. Now, if you recall our limit laws, we can actually move, we can move our limit through the cube root. So I'm going to rewrite this as a cube root. So I'm going to cube root after I find the limit as x approaches infinity of 6x plus 5 divided by 8x minus 3. So we again look in our denominator, and the largest exponent with the variable is x. So what we're going to do is we're going to divide our top by x and our bottom by x. So we get 6 plus 5 over x, all divided by 8 minus 3 over x. So again, these terms with the x in the denominator become 0. So now I have the cube root of 6 over 8. Can't cube root 6, but I can cube root 8. So I get the cube root of 6 divided by 2. All right, lastly, what I want to do is just to take a little bit look at infinite limits at infinity. So the notation f of x equals to infinity as x approaches infinity is used to indicate that the values of f(x) becomes large as x becomes large. So that means our y value is becoming large as x becomes larger. So similar meanings are attached to the following symbols. So we can say limit of f of x approaches infinity as we go to negative infinity. We can have limit goes to negative infinity as we approach infinity. And lastly, the limit of f of x approaches negative infinity as x goes to negative infinity. Now we've already seen an example of this at the beginning here when we did example 3a here. So it was going to infinity as x approaches infinity. So let's take a look at some other ones which are not rational here. So find the following limits. Excuse me. So as x goes to infinity, because there's no other part, there's nothing to cancel off, we just say that this would be infinity. Now our second one seems like, well, that's a little bit odd. We have infinity cubed minus infinity squared. So would that be 0? Well, I'm going to do a little bit of manipulation here. And I'm going to say that I'm going to factor out the x squared. So then I have x minus 1. Okay. So really what I have is I have infinity plugged into here, so infinity squared, which is a very large number, and then I have infinity minus 1, which is still a very large number because I'm just subtracting 1. So here I have a very large number times a very large number, therefore I should still have a very large number. So I should have infinity. And then you guys can try the other examples, which we will take a look at later.